Let's talk about something that's at the very heart of our digital world. It's this incredible paradox. We have the technology to store just unimaginable amounts of information, but our ability to actually get that information back out, to read it, is falling so far behind it's kind of scary. So what is going on here?
Right? You can literally hold a universe of data in the palm of your hand, but then why does it feel like it takes an eternity to access it? Well, to get to the bottom of this mystery, we first need to wrap our heads around three key ideas that are creating this huge gap. To really get this, we need to look at any storage device. Doesn't matter if it's some ancient hard drive or the phone in your pocket, through the lens of three really important metrics.
Okay, so think about it like a library. Capacity? That's easy. It's just how many books you can fit on the shelves. Throughput is how fast you can read, how many words per minute. And then there's latency. That's the time it takes you to actually get off the couch, walk over to the shelf, and find the book before you can even read that first word. Now, these three things are in a constant race with each other. And as we're about to see, one of them is winning by an absolutely unbelievable margin.
So let's see this race in action. We're going to compare one of the very first hard drives from way back in 1956 with a modern solid-state drive from today. And I promise you, the difference is going to completely blow your mind.
Now, what's really fascinating here isn't just the numbers on the screen. It's the physical reality of it. That old 1956 IBM drive, with its measly 5 megabytes of storage, it was over 1.5 meters tall. I mean, you couldn't even fit it in this room. The modern drive, 245 terabytes, and it fits right in the palm of my hand. The change in scale is it's staggering. And when we actually visualize that growth, the problem becomes terrifyingly clear. Look at that. Our storage capacity has improved by a factor of roughly 1 trillion. But our throughput, our speed for reading it, has only improved by a factor of 1 million. That means there's a million-fold gap between how good we are at storing data and how good we are at reading it. We've basically created this monster that we can't keep up with.
To really feel the impact of this gap, let's translate it into an analogy that you are not going to forget. We're going to apply this exact same problem to something a little more familiar, just reading a book.
So here's the setup. We've increased the book's capacity, how many words are packed onto each page, by that same insane trillion times factor. And to be fair, we've also improved our reading speed by that million times factor. So we can read much, much faster, but the book itself is just incomprehensibly dense. So, logically, you might think it would still take 10 hours, right? The ratios should kind of cancel each other out. But because of that massive million-fold gap between capacity growth and throughput growth, the answer is not 10 hours. It's not even 10 days.
287 years. That is how long it would take you to finish the book. And this just perfectly illustrates the crisis we're in. We can build these vast, incredible libraries of information, but we've built a system where we physically cannot read them back in a human lifetime. It's wild.
So, how in the world do you solve an impossible problem like reading a 287-year book? Well, you don't. You change the rules of the game. You don't try to read it faster, you have to read it smarter.
And this, right here, is the fundamental idea behind all modern data centers. It's called parallelization. You don't put all your data on one giant slow device. No way. You shred it. You spread it across thousands of smaller devices. And then, here's the magic. You read from all of them at the exact same time. It's the only way we can possibly overcome that massive throughput gap.
But this brilliant solution, parallelization, it creates a new kind of sneaky problem. It's something we can call the startup cost of reading each one of those million tiny little pieces.
Come on, we've all been there, right? Staring at that progress bar that's just stuck. That exact experience, that frustration, holds the key to understanding the next huge challenge that data centers had to figure out.
Remember latency? That little wait time before the data actually starts flowing? Well, when you're reading one giant file, you only pay that penalty once, right at the beginning. But when you're reading 1 million shredded pieces, you have to pay that latency tax 1 million times. And each of those little pauses, they add up and they absolutely grind your incredible speed to a halt.
So here's the crucial point. Data centers don't ask for one tiny piece at a time. That would be crazy inefficient. Instead, they group or batch thousands of requests together into one bigger request. And by doing this, they can manage that latency tax, keeping the whole system humming along even when they're dealing with millions of separate pieces of data.
Okay, so let's put it all together. Let's see how all of this, the capacity gap, the parallelization, the batching, gives us a much clearer idea of what that famous buzzword, big data, actually is.
We've just walked through the entire core challenge, right? It's not just that the data is big. It's that there's this massive physical gap between how fast we can store it and how fast we can access it. Big data is really the story of how engineers got clever and found a way around that fundamental gap.
And this, right here, this is the key takeaway from our whole explainer today. Big data isn't the data itself, not really. It's the entire ecosystem of amazing technologies, the data centers, the parallel processing, the batching systems, all the stuff we had to invent to make those massive data sets actually useful in the first place.
It's crazy to think about, but we literally had to invent new words, Rona and Quetta, because we were running out of prefixes to describe how much data we're storing. As we keep pushing into that future, this race between storage and access is only going to get more intense. The only question is, what's the next seemingly impossible problem going to be? And what brilliant ideas will we come up with to solve it?